Welcome back to our course on quantitative analysis for management decision. If Module 1 was about learning the language and grammar of quantitative decision-making, Module 2 is where we start writing our own sentences, or in this case, our own solutions. We're now moving beyond the what and why into the how. How do we take raw numbers and transform them into clear, actionable recommendations for a manager? How do we decide between multiple investment options? How do we schedule limited resources for maximum efficiency? And how do we anticipate future conditions before they happen? By the end of this module, you'll be able to not only interpret quantitative results but also apply a range of techniques to solve specific business problems. 2.1 Quantitative Models, the Manager's Decision Toolbox. In the business world, a model is simply a structured way of representing a real-world problem so that it can be analyzed and solved. Think of it like a flight simulator for pilots. It's not the real airplane, but it allows you to test situations safely and cheaply before making real decisions. There are three major types of quantitative models we'll focus on. Descriptive models. These models organize and summarize data so we can understand what's happening right now or what happened in the past. Examples: sales dashboards that show revenue by region, customer segmentation reports, financial statement analysis. Descriptive models don't tell you what to do, they just tell you what is. Predictive models. These use historical data to forecast future outcomes. Examples: predicting next quarter sales, forecasting demand for a product, estimating the probability of loan default. Prescriptive models. These go beyond prediction, they recommend specific actions. Examples: determining the optimal price for maximum profit, allocating advertising budgets across different media channels, planning transportation routes to minimize cost. 2.2 Optimization techniques. Optimization is about finding the best possible solution given the constraints you face. In business, constraints might include limited budgets, time, labor, raw materials, or regulations. Common optimization approaches include linear programming, LP. Used when the relationship between variables is linear and both the objective function and constraints can be expressed as linear equations. Example: a factory deciding how much of each product to produce to maximize profit without exceeding production capacity. Integer programming. Similar to linear programming, but the decision variables must be whole numbers. Example: assigning workers to shifts, you can't assign half a worker. Goal programming. Useful when there are multiple objectives to achieve simultaneously. Example: a company wants to maximize profits but also minimize overtime hours and keep customer wait times low. Nonlinear programming. Applied when the relationship between variables is not linear, common in pricing strategies and engineering design. 2.3 Decision analysis under uncertainty. In many real-life cases, we don't have complete certainty about the future. That's where decision analysis comes in, a systematic way to evaluate options when outcomes are uncertain. Key tools. Decision trees, visual maps that lay out possible decisions and their outcomes, along with probabilities and payoffs. Expected value analysis, calculates the weighted average of all possible outcomes, using their probabilities as weights. Sensitivity analysis, test how changes in assumptions affect the final decision. Example: a retailer deciding whether to expand to a new location might use a decision tree to consider different market conditions, booming, stable, or declining, and estimate the profits in each case. 2.4 Forecasting methods. Forecasting is about predicting future values based on past and present data. It's crucial for planning production, budgeting, staffing, and marketing campaigns. Types of forecasting. Qualitative methods. Useful when historical data is limited. Examples: expert opinion panels. Delphi method, structured rounds of expert input. Market research surveys. Time series methods. These use historical data collected over time. Examples: moving averages, exponential smoothing, trend projection. Causal models. These assume that the variable being forecasted has a cause-effect relationship with other variables. Example: Sales might be predicted based on advertising spend, economic indicators, and seasonality. 2.5 Simulation in management decision-making. Sometimes, the best way to understand a complex system is to simulate it. Simulation involves creating a computer-based representation of a real process and experimenting with it to see how changes affect outcomes. Examples. Monte Carlo simulation runs thousands of random scenarios to estimate possible outcomes, often used in risk analysis. Inventory simulation models demand fluctuations to test inventory control policies. Financial simulation models investment portfolio performance under different market conditions. Simulation is particularly valuable when the system is too complex for analytical solutions. Experiments in the real world would be too costly or risky. There are many uncertain factors. 2.6 Inventory and supply chain models. For companies dealing with physical goods, managing inventory is a balancing act. Too much stock means high holding cost, too little means lost sales. Key models. Economic order quantity, EOQ, determines the optimal order size to minimize total cost. Just-in-time, JIT, minimizes inventory by receiving goods only when needed. ABC analysis classifies inventory items into 3 categories. A equals high value, low quantity. B equals moderate value, moderate quantity. C equals low value, high quantity. Supply chain models extend this thinking to the flow of materials from suppliers through production to customers. 2.7 Project management and quantitative analysis. Projects, whether launching a product or building a new facility, require planning, scheduling, and resource allocation. 2 key quantitative tools are: Critical Path Method, CPM, identifies the sequence of tasks that determine the minimum project duration. Program Evaluation and Review Technique, PERT, estimates project timelines when activity durations are uncertain. Both help managers allocate resources efficiently, anticipate delays, and keep projects on track. 2.8 Real-world case applications. Let's connect all of this to real-life situations. Case 1, Airline scheduling. Airlines use optimization models to assign planes to routes, crew to flights, and set ticket prices dynamically based on demand forecast. Case 2, Retail stocking decisions. Retailers like Walmart use predictive analytics to forecast product demand, ensuring shelves are stocked without excessive overstock. Case 3, Hospital resource allocation. Hospitals use simulation to plan for patient inflow during flu seasons, optimizing staff schedules and bed availability. Case 4, Investment portfolio management. Financial firms use Monte Carlo simulations to model how portfolios might perform under different market scenarios. 2.9 Ethical and practical considerations. Quantitative analysis is powerful, but it's not foolproof. We must always ask: are the data accurate and unbiased? Are the assumptions reasonable? Could the model's recommendations have unintended consequences? Does the decision align with organizational values and ethics? For instance, an algorithm might recommend laying off workers to cut costs, but managers must weigh social impact and long-term brand reputation. Wrapping up Module 2, we've explored descriptive, predictive, and prescriptive models, optimization techniques, decision-making under uncertainty, forecasting methods, simulation applications, inventory and supply chain management, project management tools, real-world case applications, ethical considerations. At this point, you have both the foundation from Module 1 and the applications from Module 2. This means you can now not only understand quantitative analysis but also apply it in real managerial contexts, making you far more equipped to guide organizations toward informed, data-driven, and effective decisions.